So friends, welcome back to our thermodynamics discussion. In this episode, we will see Joule-Thomson effect. James Prescott Joule conducted an experiment to measure the internal pressure, that is change in internal energy with respect to change in volume at constant temperature. That is what is internal pressure. We have seen this in a previous section. And he wanted to measure internal pressure by measuring a change in temperature in case of a free expansion as shown here. You've got two chambers. He took a system like this where these two chambers are separated by a valve like this, and the first chamber is filled with air at high pressure and the second chamber here is maintained at vacuum. And the whole system is now kept in a water bath, and the apparatus or thermometer was connected to measure the change in temperatures occurring in the water bath. What happens is change in temperature or temperature of the water bath before and after the valve was opened was measured. And this is a case of free expansion, that is the gas is expanding from this high pressure region to this vacuum region. That is, in this free expansion case, we have already seen in the previous section that the work in such case will be zero. And the James Joule, when he measured the temperature difference before and after the expansion, was a zero. That is, he measured no change in temperature. So, heat evolved during the processes also zero. That is, change in internal energy. When there is no change in temperature, you can reach the assumption that change in internal energy is zero. That is, the change in internal energy that he measured during this volume change or during this expansion at constant temperature is zero. That is, the internal pressure at constant temperature in this case is zero. That is what the observation Joule obtained from this experiment. But actually, although this experiment produced a very important information there, the internal pressure or change in internal energy with respect to volume at a constant temperature case is zero. He established this through this experiment. But actually, this experiment is crude. In what sense? As the heat capacity of the whole apparatus he used, the heat capacity of the apparatus in which he contained the gases, the heat capacity was too high that a small change in temperature, although there was a small change in temperature during the process, will not be reflected because the container of the gas had huge heat capacity such that any small change in temperature will not be reflected. Beyond the crudeness of this experiment, the experiment produced a very interesting observation which is called Joule-Thomson effect. Here, you've got an experimental setup where the gas chamber is there and this chamber is divided into two by using a porous plug. Okay, and on one side, the gas is maintained at very high pressure, and the other side of the plug, it is at low pressure, and the whole system is insulated. So, a adiabatic condition is maintained. So, on the high pressure side, we have got the initial pressure, volume and temperature conditions marked by Pi, Vi and Ti, and at the low pressure condition, you have respectively Pf, Vf and Tf for the pressure, volume and temperature values. And now, when the gas expands, this is an irreversible expansion because the pressure on both sides are not equal. So, one is at high pressure and the other is at low pressure. So, it is obviously an irreversible expansion and is adiabatic. You see, this is insulated chamber. So, the expansion is adiabatic, irreversible. And during expansion, adiabatic irreversible expansion, the work is done at the expense of internal energy. Again, we have seen this in one of the previous lectures. If you want, you please go and refer to that section. Work in case of adiabatic irreversible expansion will be done at the expense of internal energy. That means a part of internal energy is used in this expansion, and this will obviously lower the internal energy, resulting in lowering the temperature. That means cooling occurs during this kind of expansion. That is when irreversible expansion occurs through a porous plug in an adiabatic condition. You can see that cooling occurs, and this is how you can explain that cooling. That is, in adiabatic irreversible expansion, the work is done at the expense of internal energy. This results in a lowering in internal energy, and obviously the temperature falls, and that means you can observe cooling. And this observation is called Joule-Thomson effect. Now we will see what happens or what is the nature of the work. Work done, there are two chambers, one maintained at high pressure and one maintained at low pressure at the beginning, and those two chambers undergo certain work during expansion, and the work in the first chamber is given by this expression, that is PIVI here, and similarly work in the second chamber will be PFVF. Okay, and so the total work done during this whole process will be the sum of the two works, W1 and W2. So you get the total work is PIVI minus PFVF from this calculation described above. Now, you observe a change in internal energy because the work is done at the expense of internal energy. So the change in internal energy during the process, that is the difference in internal energies before and after, that is final and initial, will give you the work, and that work corresponds to this value. And you can rearrange this equation to get this form, that is UF plus PFVF equals UI plus PIVI. On the left hand side you have got an expression for enthalpy final condition, and on the right hand side you have got expression for enthalpy on the initial condition. So you can say there during the process there is no change in enthalpy. Final and initial enthalpies are the same. That is, the Joule-Thomson expansion occurs in isenthalpic condition, or the process is isenthalpic. The enthalpy is constant. So you can define Joule-Thomson effect or expansion to be cooling of a gas by isenthalpic expansion. And during that expansion, the temperature difference occurs against a pressure difference. So the temperature difference corresponds to the pressure difference, or the temperature difference is proportional to the pressure difference. That means you can write it like this: the ratio between the temperature difference to the pressure difference at constant enthalpy. We have seen this is an isenthalpic process. So this ratio of change in temperature to change in pressure at constant enthalpy can be called as Joule-Thomson coefficient, represented by mu Jt. And so the definition for mu Jt is change in temperature with respect to change in pressure at isenthalpic expansion, or any isenthalpic process, expansion or compression it can be. And for ideal gases, Joule-Thomson coefficient is a 0. And for real gases, ideal gases and real gases differ mainly because of the nature of intermolecular interaction. For ideal gases, there is no intermolecular interaction at all, but for real gases, there is significant intermolecular attraction or repulsive interactions. For real gases, the Joule-Thomson coefficient depends on a number of factors, including the nature of the gas, the chemistry of the gas, the pressure condition, and the relative magnitude of attractive and repulsive forces, the intermolecular forces, and therefore the Joule-Thomson coefficient mu Jt can be positive or negative depending on all those parameters. Positive mu Jt says as the pressure decreases, the temperature also decreases. That will give you a positive mu Jt, and that is the case of cooling during expansion. When expansion occurs, that is when pressure decreases, temperature also decreases, that is cooling occurs. And all the gases except hydrogen, helium and neon cools on expansion at room temperature. That is, at room temperature, all the gases except for these three, you can see a positive mu Jt. And case of negative mu Jt as a case where temperature increase when pressure decrease, based on this equation here. That is, gas heats on expansion, and gases like hydrogen, helium and neon heats on expansion at room temperature condition. So we can say obviously the mu Jt, whether it is positive or negative, or what is the value of the Joule-Thomson coefficient, is dependent on temperature. So Joule-Thomson coefficient is temperature dependent, and now we will see the temperature dependence of Joule-Thomson coefficient. And the sign of Joule-Thomson coefficient, from negative to positive it changes, or from positive to negative it changes at a temperature called inversion temperature. And at inversion temperature, the Joule-Thomson coefficient is a 0. Like this. This is a graph for nitrogen gas, and the pressure dependence of temperature is shown here. If your case, for example, look at 200 bar pressure. At this pressure, you can see around 100 degree, from temperatures around 100 Kelvin to around 500 Kelvin, you can see the Joule-Thomson coefficient is greater than 0, that is positive. And below this temperature 100 and above this 500, you can see the Joule-Thomson coefficient is negative. So there are two inversion temperatures. The sign changes from negative to positive around 100 degree and from positive to negative around 500 degree. So in both at both these temperatures, both these inversion temperatures at the given pressure of 200 bars, you can say there are two inversion temperatures, and at these two inversion temperatures you measure Joule-Thomson coefficient 0. And only for a given range of temperature you see a positive mu Gt, that is gas cools on expansion. And below the first inversion temperature, gas heats on expansion, and beyond the second inversion temperature, gas heats on expansion. So this is how we understand Joule-Thomson effect and its temperature dependence. And now we will see the intermolecular interactions, or what happens in the molecular level when the Joule-Thomson expansion or Joule-Thomson effect observes. Consider the case where intermolecular interactions are dominating over the repulsive interactions. That is, in the beginning, when the gas is present at relatively high pressure, the molecules are in good relation there, the attractive forces are dominating, and when you want to expand the same molecule, same gas to a low pressure region, to a larger volume, these molecules should move apart from each other against this intermolecular force. So there is some work is to be done against the intermolecular force so that the molecules are moving apart from each other to occupy this larger volume. So the molecules move against the attraction. That means it requires energy, and that energy is consumed from the internal energy. That means a part of the internal energy is consumed, means you can observe a change in kinetic energy. Obviously, temperature falls, resulting in cooling. So when intermolecular attractions dominate over repulsion, the gas in the attractive state, when they expand to a larger volume, needs to do work against the attraction. So internal energy is consumed, temperature falls, and you can see a positive Joule-Thomson coefficient is observed. Cooling occurs when expansion occurs. On the other hand, if you have got intermolecular repulsions dominating over attractions, already when at high pressure they are not in good relations, that the molecules are already okay to stay at larger distance. But when the gas is expanding, you ask the gas to expand to a larger volume, that is to low pressure, they move apart happily, they move faster than before. That means molecular velocity increases, resulting in an increase in kinetic energy. Obviously, the internal energy increases and temperature of the whole system rise, resulting in heating. That is what occurs in this case where intermolecular repulsions are dominating over attractions. In the end, you have got an increase in kinetic internal energy and hence a temperature rise, heating. That means the Joule-Thomson coefficient will be negative. This is what is the molecular level understanding of Joule-Thomson effect. And in terms of van der Waals coefficient, van der Waals equations or van der Waals modification of ideal gas equation for real gases includes two terms, the pressure correction and volume correction A and B, considering the intermolecular attractions or generally intermolecular interactions in the real gases. So in terms of the pressure and volume corrections A and B, you can express the inversion temperature, that is the temperature at which Joule-Thomson coefficient changes its sign, or Joule-Thomson coefficient stays 0, is related to A and B like this through R, 2A by RB. R is the universal gas constant. And now we will see a different expression. You can say generally enthalpy is a function of temperature and pressure. Therefore, change in enthalpy during a process can be expressed as a partial derivative of enthalpy with respect to temperature at constant pressure and partial derivative of enthalpy with respect to pressure at constant temperature. And from this expression, you can deduce something. This part, we have seen this is defined as the heat capacity at constant pressure. Change in enthalpy with respect to change in temperature at constant pressure. So you may write this equation in terms of heat capacity. And the Joule-Thomson expansion is an isenthalpic expansion, that is, change in enthalpy is 0. So equating this expression to be 0 and rearranging, you can reach this expression, and the change in temperature with respect to change in pressure at constant enthalpy, that is, from this equation you get this form, but this part is our Joule-Thomson coefficient mu Jt, the change in temperature with respect to change in pressure at constant enthalpy. This can be equated to this RHS, that is minus 1 by Cp, infinitesimally small change in enthalpy with respect to pressure at constant temperature. Combining these two forms, the first and very last form, you can reach this equation. Change in enthalpy for any general process can be expressed in terms of its heat capacity and Joule-Thomson coefficient like this. And Joule-Thomson expansion is a special case of this equation where you apply the change in enthalpy is 0, the process occurring at isenthalpic condition. Now we move on to see the applications of Joule-Thomson effect. The most important application is liquefaction of gases. Gases can be liquefied. Gases can be converted to liquids when the intermolecular attractions are sufficient enough to form to correspond to the liquid state. When you have got gases moving at very high velocity, but if you can somehow decrease the molecular velocity of gases, the molecular velocity, when you see the molecules come, when they are moving with lower velocity, they come closer and closer to develop intermolecular interactions or attractions, and when these attractive forces are sufficient enough to form liquid state, you get liquids. Likewise, you can convert gases into liquid. Two processes are there, mainly Linde's process and Claude's process. In Linde's process, what you are doing is, you've got gas and you pass this gas through this coiled part, and at the end of this coiled structure, you have got a throttle like a porous plug, and so the gas is expanding from this coil to the outside across or through the porous plug. Obviously, cooling occurs, Joule-Thomson expansion, cooling occurs. And what happens is, this cooled gas is again pumped through this part again through a compressor. It is compressed, the cooled gas is now compressed to a high pressure. Then again the same happen. Again it passes through the coil structure, expands through the throttle to a cooler gas, even cooler gas you obtain. And this cooler gas again is passing again through the same cycle. You get even cooler and cooler gases are obtained at every step of this expansion. And at certain point you get the very cold gas is converting suddenly to liquid, because this very cold gas is having sufficient intermolecular attraction, and when it is further cold, the intermolecular attraction become even stronger, that it forms liquid. That is the principle of Linde's process of liquefaction. And now we will see Claude's process. In Claude's process, two things happen actually. Along AB, it comes here, and At C, it is splitted again, and at C, when the gas goes down to this coil structure, it expands at this throttle. The Joule-Thomson expansion occurs. The temperature of the gas decreases, and it further goes up, and at this part, it goes through this part of the structure and enters the compressor, and again it comes downward along AB. And at C, what happened is the gas is split into two, and at C, downward you get the Joule-Thomson expansion, and along this direction the work is done at the expense of internal energy. So the gas comes down cooling because the internal energy is used. So these two processes, the Joule-Thomson and the other side here, this expansion, these two contribute to the cooling of the gases. And this cool gas is now taken again to the compressor like this, and the process repeats. And at certain point, you get the cooler and cooler gas now converts to liquid at certain moment. This is how you can liquefy gases in two ways, either in Linde's process or in Claudius process, both using Joule-Thomson effect as the basic principle to get liquid from a gas or to convert gas into liquid. That's all about Joule-Thomson effect and its applications on liquefaction of gases. And in the next session, we will see thermochemistry, the enthalpy changes and energetics of chemical reactions. And until then, thank you and bye-bye.